Okay, can everybody see the screen?
Yeah, that's perfect. Thank
Okay,
you.
good.
I'll introduce myself. Uh,
Okay,
so welcome everybody to this seminar that is organized by UNSW. It's also part of the Statistic Across Campuses initiative, and it's also jointly organized with the Environmental Statistics section of the Stat Society of Australia, and this is the December Environmental Stats Seminar. So today we are very happy to have Subhash Lele from the University of Alberta. So Subhash is a professor, or now emeritus professor since he's retired. His research interests are in statistical inference, hierarchical models, MCMC methods, but also statistical ecology, population dynamics model and inference, and etc. Like other things like measurement error, spatial data. Yeah, that's a summary of Subhash's research interest. And today he's going to talk about occupancy and abundance surveys in the presence of detection error, so a review and critical comparison of methods. Subhash, thanks for taking the time to give this talk, and the floor is yours.
thank you. Can everybody hear me okay? Anybody?
Yeah, that's fine.
Okay, good. All right, so here is what we are interested in general. This is a very general talk, not a particular data set. So in general, in ecology, we want to estimate abundance of a particular species in a given study area, or sometimes you cannot count the number of animals. So what you can say is the species present or not, and what proportion of the area is occupied by the species. So the goal is to know what is out there, and if you know that, then you can manage it. So this is just an area in northern Alberta, and the dots is where you probably would go and do some kind of a survey. And so you have data from those dots, and from there you have to somehow predict what the average abundance will be over the entire purple area, or you may want it at any of the locations in terms of spatial distribution. And the same thing applies to occupancy. And this is important for monitoring as well as management. So that's my general introduction to the topic. Now I'm getting into statistics, basically. So this seems like a pretty standard statistical problem. What would a statistician do? We will go out, sample some of the sites. At each site, I will go and observe either the number of individuals, or if I'm looking for occupancy, I would say, did I see at least one individual or no individuals? And so it turns into 1 or 0 situation, or number of individuals. It really depends on the species, which one you can do or which one you want. And given this particular problem, it is pretty straightforward to see what one would do. If I want to estimate occupancy, I may relate the presence of a species, y equal to 1, to some covariates. We know how to do binary regression. So psi x beta could be a logistic link or whatever link you want to use to relate covariates to the occupancy. Or if you have abundance, a standard model will be Poisson regression model or some other discrete model. So this seems to be a pretty straightforward problem. And if I have the data, I can estimate the parameters, predict the occupancy status, or number of individuals at the unsampled sites, fairly straightforward. However, there is a major difficulty in doing what we just said, and that is of detection error. So when I go out and try to count all the birds, it's easy to say that count all the birds within, say, 100 meters of where you are, or whatever the sampling criterion might be. But it's not that easy, because you don't see the birds many times, you hear them. And if a bird is not singing, I'm not going to see the bird. Or if it is raining, the birds may not be out there. Or if I go in the afternoon, being a statistician, I don't know anything, I might go in the afternoon after my lunch, and I won't see any birds because they are not out there. They are usually active in the morning. And so when you go, you may not see all the birds that are out there. And so you won't count all the birds. You only get a subset of the birds that are out there. And the same thing is with presence absence. Even if it is there, I may not see it because it is hidden behind something, or who knows. And so it is easy to say, just go and check if they are occupied or not, or count the number of birds. You have to take into account this kind of detection error, where even if the individual is there, you may not see it and note it as 0 instead of 1. And if we do that, you may get in trouble. So that's what I want to talk about. So I'm going to ignore lots of difficulties that are there in ecology about the singing rate and how far is my audio detector recorder recording and things like that. I'm going to go very, very simple. And so the idealization is basically this. If I consider Y as a true status at location, and I'm going to talk about occupancy initially, it is easy to talk about. So 0 means unoccupied, 1 is occupied. The observed status at location, Wi, could be 0 or 1. What's the distribution of that Wi? This is pretty straightforward. Occupancy probability, as we said, Yi could depend on the habitat covariates. You can use logistic regression or whatever. Let's call it psi I. It may change from location to location. What about the detection probability? So if there is an individual, sometimes I may see, sometimes I may not. So if there is an individual, what is the probability that I detect? So I call it Pi is the detection probability. And you can model it again depending on the covariates that may be same as Xi or something else, depends on the situation. And so that is Pi, and Wi given 1, if there is no individual there, I'm not going to have phantom individuals. So that's the assumption that I'm going to make. 0 is always noted as 0, but 1 could be either 1 or 0. So that is the detection method that I have. So we can, given this, I can easily calculate the marginal distribution of the observed data. So probability of Wi equal to 1 is, it should be there, so psi I, times it is detected, which is Pi. So I will observe 1 if it is there and it is detected. So it is Pi times psi I. Naturally, Wi equal to 0 is 1 minus Pi psi I. And if they are constant, a simple situation, then it will be P times psi and 1 minus P times psi. Obviously, if we ignore that there is detection error, our occupancy rate will be based on the estimate of P times psi, because I will count how many occupied. Proportion of occupied in the sample is a good estimate of P times psi, the standard MLE, but that is smaller than psi. And so if P is far away from 1, you could be in trouble. You might say there aren't enough individuals out there when actually there are. This may be good for the environmentalists, but industry people will sue you if you don't adjust for this. And so we need to adjust for this detection error for various reasons, because we don't want to mislead people. So if the probability of detection is close to 1, maybe it is better not to adjust for detection error and behave as if there is no detection. Because if you try to estimate this nuisance parameter of P, the detection error, you will lose information in that, and it can lead to further problems about the variation in the estimator of the occupancy. So if it is close to 1, usually we just ignore there is no problem of detection, and you could just use it as is. So medicine can be worse than the disease if you adjust. So better not to adjust. But usually p is not close to 1, so we adjust, and any adjustment for detection error will reduce the bias in the occupancy estimator, but it will necessarily increase the variance of the estimator. So we have to balance between the two. Okay, so how do we use it? Suppose we can estimate the detection error, then we can estimate or predict actually the occupancy of a site that is observed to be 0. So if I observe W, what's the chance that it was actually occupied? And you can use the standard conditional probability rules that you are aware of, and I can write it as 1 minus p times psi divided by 1 minus p psi. And so I'm dividing by a number smaller than 1. So I have to be careful when I do this. If that number is not well estimated, I could get in trouble in terms of prediction error. And the sites that are not sampled at all, we don't have W's, so we just predict them as P. And then we sum all the P's, sum of all these numbers and the ones, and we can calculate the total occupancy rate for the entire study area. We could include the covariates in this in a fairly simple fashion if we know the parameters. So I'm not going to discuss that in this context. So how can we estimate the detection error is the question. So anybody who has worked on measurement error would be familiar with the way people do. You take a sample, send it to the lab by splitting it into two, ask them to find out what the value is. And if the two values are different, we know there is a measurement error because we send the same sample. And the difference from the truth to those measurement errors, to the observations, give us the measurement error. The same way we could do for these occupancy surveys. So we go to the site and suppose it is occupied because we see something. So we know it is occupied. And then I go there next time and I see there is nothing. So it could be because it actually changed the status, or it could be detection error. So to avoid the possibility of change of original status, the assumption that is made in these kinds of surveys is that the true occupied status does not change during the replicate visits. So I'm saying that the true status is the same, but the observed status could go from 1 to 0, depending on if the true status is 1. If it is 0, it is always going to stay 0. And so we can use this change in the observations should give us the idea of probability of detection. And so what are the assumptions to do this? So that we assume the usual surveys are independent of each other. We do not double count. We do not see the species when it is not there. And the fourth assumption is the key assumption that the population is closed. So there are no births, no deaths, no immigration, no emigration of any kind. So that's the closed population assumption that is critical in order to use this. Now, if we assume that, and now suppose I have R multiple surveys, can you see my, I hope you can see the pointer. If not, let me know. So suppose we do R surveys, then we can observe the location to have been occupied in one of those surveys. Then we know by closed population assumption that it was occupied all through, because it was occupied once, it is occupied always. And hence the likelihood component for the location that was observed to have been occupied at least once is basically it was occupied with probability psi I times probability it was occupied, observed to be occupied, wij times. So pij times to the power wij, 1 minus pij to the power wij, and I multiply over j. So this is the likelihood component for the location where I have observed at least once. Now, if the site was never observed to be occupied, this could be because it was unoccupied, so I'm never going to observe, or it was occupied but never detected. So it's basically psi I times all the time I missed it. And so you can combine all these terms and write down the full likelihood to get the maximum likelihood estimators. And it's pretty straightforward to do that. We all know how to do basically likelihood estimation, or that's what I'm assuming. So to understand why these multiple visits allow us to estimate detection error, we'll look at those locations where we have observed the location to be occupied at least once. So I'm only considering the subset of that. In that case, because it was occupied once, I know the changes 0 to 1 conditionally are only because of the detection error. And so the conditional likelihood only depends on Pij's. And so this tells me that I should be able to estimate detection error as long as my closed population assumption is satisfied. So an occupied should remain occupied, unoccupied should remain unoccupied. So the changes I see are only because of the detection and nothing else. And in that case, you can estimate the detection probabilities. And if you can do that, the rest is easy to do. So this is simply a binomial likelihood. We know we can do that. And once we do that, we can do the full likelihood. At least we know it is estimable, and we can do the rest. And this can be generalized to abundance surveys, where the true abundance, maybe I can model it as Poisson lambda I. This depends on the covariates. Observed abundance is Yij. Now you will never observe bigger than Ni, so that's why it is binomial with Ni. So each trial and each individual has, oh, this should be Pij, has probability Pij of coming in my sample. So I'm assuming the individuals come in my sample independently of each other, which may be troublesome, but we are going to live with that for now. Well, given this, I'm not observing N, so I have to write down the marginal likelihood based on the observed data, which is Yij. And I can write it using the mixture likelihood, which is probability of Y equal to Y. I have to sum over all possible N's, but I know N has to be bigger than Y because I have already observed Y. And so I sum it from Y to infinity, probability of Y equal to Y, N equal to N times probability of N equal to N. This is standard mixture thing, and we should be able to sum this. So this is called N mixture model. This is basically a binomial Poisson mixture. And again, once you have the model, you have the marginal distribution, you write down the likelihood, obtain the maximum likelihood estimators of the abundance, and we are in good shape. This can be generalized to negative binomial, zero inflated Poisson, and so on and so forth. So if you have replicate surveys, and if you have closed population assumption that says that the occupancy status does not change, or the number of individuals in that area does not change during my repeat surveys, theory is pretty straightforward. I'm not saying it is trivial. It is a great idea, but easy to do as a statistical problem. So it is theoretically sound, very intuitive. It's been extremely popular, widely used in practice. So we should be happy and go drink beer like all Australians do. Unfortunately, life is not all beer. So what is the problem? So one question that naturally comes up is, how many surveys do I need? And it turns out if the probability of occupancy or probability of detection is small, well, you are going to need lots of surveys. And it can be from anywhere from 5 to 25. And imagining going there so many times and making sure they are closed, it's difficult. So the problem with these multiple surveys is that the cost is prohibitive, especially living in northern Alberta. The traveling cost is dangerous. You may have to take the helicopter to go in and whatnot. And so multiple surveys are not easy to conduct logistically as well as monetarily. Sometimes you can survey animals only during a very, very short period. Like the moose surveys I work on, you can only do for two weeks in November when there is snow, but not too much snow. So it is like a Goldilocks problem. You have to go just at the right time. Otherwise, you won't see them at all. And so this can be difficult. And then the natural question is, do I spend lots of time on few sites so that I get the detection error very well, but then I cannot extrapolate it further. So I want to visit lots of sites. But if I go to lots of sites, I don't have enough money to go there repeatedly. And so there is again the problem of matching or balancing the two situations. And given all these, the closed population assumption is the most difficult assumption to satisfy. And birds do fly, birds die. And so, or they come in, especially singing songbirds type migration birds. So that becomes really difficult to satisfy. So what do we do? Or what effect does it have? And I'm not going to show you all of it because my goal of my talk is slightly different. But it turns out that even a minor violation of that assumption leads to substantial bias. So here is a quote from a paper that one of my colleagues wrote. He was working on dark-eyed juncos, and he said, without adjusting for the detection error, the density was 0.25 birds per hectare in control, 0.38 in thin stands. So thin stands have a slightly higher. After adjusting for detection error under the closed population assumption, he estimated 2.22 and 3.67, almost 10 times increase over the raw counts. Whoa, that detection error must be important here. But if you look at biology behind this, and they have other studies on juncos, they generally have density of 0.65 or so. And so this seems way out of what we would ever observe. So that might be because the closed population assumption is not satisfied. And so even it turns out he has done simulations and he has shown that even a minor violation of that assumption can have a problem. So what can we do? Well, ecologists say, I don't know what to do. There is no alternative, so I'm just going to use it. And now there are alternatives, of course, but at that time there wasn't. So I asked purely mathematical question to begin with. Suppose I had only one survey, then I know it is closed, almost. I mean, close to being closed, I would say. So what can we estimate in that particular case? Or when can we estimate detection error and occupancy or abundance using only single survey? Is there a condition that I can come up with? Maybe we could think about it, doing that. And if the answer is never, mathematically it cannot be done, then we are stuck with doing replicate surveys and try to make them as efficient as we can. Fortunately, mathematically the answer is yes, if there are a few conditions as usual. So what are the conditions under which you could do that? The first condition is that there should be covariates that affect occupancy and covariates that affect detection. So they cannot be constant. That's the major assumption, but that's not that unusual because usually there are covariates that we use to monitor things. The set of covariates that affect detection and the covariates that affect occupancy, they should not be completely overlapping. Then you cannot separate it. So there should be some covariates that only affect detection and that affect only occupancy. And this happens quite often in real life, and many of the examples actually they are separate. So there is no commonality. And the third assumption is kind of tricky. The probability of detection error should be nonlinear on the logarithmic scale. And it turns out the usual link function for binary data, like logistic, complementary, log-log, do satisfy this condition. So although this looks like an awkward condition, it's not that awkward because almost every link function that I have come across that is used in practice satisfies the condition. Okay, so it seems this affirmative answer is very counterintuitive. So given only one survey, we know the likelihood of the observed data will be based on PICI, the product of these two functions. And if we can only observe the product, how can I decompose them into individual components? Is this too good to be true? So I'm going to show you how this works out. Oops, sorry. I'm going to change my. I opened the wrong file. Up to this, it was okay. I'm going to get the right file here. Sorry. Okay, can you see my file? Can you see the screen still, Boris?
Yeah, that's perfect.
Okay, sorry, I had to change the file because I had created a shorter talk and forgot to put that file. I put the original one. Anyway, so in the occupancy surveys, we saw that we can estimate the product Pi times Ci, and I can write it as P of Zi delta, where Z are the covariates that affect detection, psi of Xi beta, where these affect the detection. So I'm going to call this function as H of Zeta Xi for now. And so suppose I fix the covariates for detection, then I know I can estimate this ratio, psi of Xi beta divided by psi of Xi prime beta, some other value of the covariate. So I get the relative change in the probability of detection, or in this case, probability of occupancy. And the same thing can be applied for probability of detection. So given single survey, I don't really, I can estimate this product, and I can also estimate this ratio. The question is, given this ratio, can I estimate the parameters beta? One clear constraint that I have is that if psi, I can change it with C times psi, then that C is not going to be estimable. So the scaled version of this is not going to be estimable. So it's not a completely general function. There is some constraint that I have to put in, especially with this scaling. So what is that? So I'm going to restrict the class of models so that scaling is not allowed. And so what happens now? So if we know the ratio, say pi, I'm just taking a general ratio, pi of x beta divided by pi of x prime beta, single covariate, just to give you an intuition. If I know the ratio, that means I know the difference on the log scale. So that's the difference on the log scale. And if I know the difference, basically I know the derivative of the function with respect to x. And so if this derivative contains all the parameters beta, then I should be able to estimate beta, because I can estimate the derivative function. It's a function of beta. So I have the empirical version of this, and I can do some kind of fitting to get beta intuitively. So here I'm not estimating the functional form that is assumed to be known, the pi component. I'm only interested in estimating the beta. So I know the link function. I want to estimate the parameter beta. And so if the derivative function depends only it depends on the entire parameter beta, then we can possibly estimate the parameters given an estimate of the derivative. And obvious corollary to this result is that any parameters that do not appear in the derivative function are not estimable. So now recall, if I had that scale function, if I take the log, that scale function gets canceled, log c minus log c. So derivative function won't involve that c, and hence I will never be able to estimate something like that. And so it turns out that almost all functions so this function class, I call it RSPF class, resource selection probability function class, and there is a history behind it that I won't be able to discuss here, unfortunately, but just call it RSPF class. So this class is all functions pi x beta that take value between 0 and 1 and are such that this log function is not a linear function in its parameters. That's what it comes down to. And so logistic model, if I take the log of it, the first component is a linear function of the parameters, but there is log of 1 plus e to the power something. And so logistic belongs to this class. And you can check all other usual link functions do satisfy this. On the other hand, if I just multiply the logistic by a constant, that scale is going to drop out. And when I take the derivative with respect to x, it becomes log c will have derivative 0. So derivative of the log function, I won't have that c, and so it won't be estimable. If the link function is exponential, and I don't know too many places or no place where exponential function is used to model probability of occupancy or probability of success. But if you use that, then only the non-intercept parameters will be estimable, because if I take the log, the intercept parameter is a constant, and when I take the derivative with respect to x, that's going to drop out, and so the derivative will only involve beta 1, beta 2, etc., but not beta naught. So link function, scale link function, or exponential won't be acceptable functions in this class. So the question is this class too restrictive? As it turns out, it is not. As I said, most of all the standard link functions satisfy this. And I have never seen a scaled link function or exponential in practice. And so I don't know if I should worry about it. But I just wanted to show you how many different forms it can take. As we know with the logit and C log, it can take a whole bunch of different forms. So it doesn't seem to be too constraining. And so we can estimate the probability of occupancy as long as we are willing to accept this particular class. If it doesn't, so this is from I forgot to remove this particular class slide. This is related to RSPF. And so the problem is that, I'm surprised. Anyway, I hope I opened it. So as it turns out that if I allow for this particular class to be my occupancy and detection, then I can split out that product and everything works out. And this class is not terribly limited. And of course, there is a possibility that the true link function is not of this type. And in that case, you are going to be in trouble. Well, I consider this as an occupational hazard of a statistician. Our analysis is only as good as the validity of our assumptions and the approximating model. And I'm going to visit this later in the talk, which is going to be an important one. So in the abundance surveys, it turns out again the same situation. I can estimate the product of P and lambda, and you can use the same logic. And if P belongs to this or RSPF class, then we are in good shape. So does it really work is something that I have to worry about. And obviously, I won't be standing here if it did not work. So I'm not even going to bother showing you the results based on this. And they are pretty old results, but we did quite a bit of simulation study and real data analysis and showed that it works. And especially if the covariates are separable, they work really well. If there are common covariates, things get a little dicey. The intercept can get somewhat dicey, so you may need quite a bit of data. So it's again the question of, do I go to several sites and do single survey, or do I go to few sites multiple times? So both have pros and cons here. So just a quick half-time summary. Detection error is present in most ecological surveys. One can control detection error using good design. One may not need or want to correct the detection error in that case. Replicate surveys could be used to estimate detection error, but they depend critically on the closure assumption aside from the logistics. And so if that assumption is violated, you may get completely bad results, and you won't know it. And so I showed that single survey in principle can be used. It avoids the closure assumption, but then it says, well, your probability functions have to be somewhat limited within this RSPF class. But as it turns out, every common link function that we have luckily satisfies that condition. So it seems to be not a significant restriction. And simulation says it works. So that said, OK, I'm good. And so I might be able to go to more surveys, and so there might be some advantages. It's a good alternative to closed population assumption. And there are other ways people have done called generalized N mixture, where you explicitly take into account immigration, and you can get in trouble because if that model is wrong, then you get bad answers. And it's hard to know if that modeling was correct or not and things like that. So I wanted to see how good this works, and it seemed to work well enough, at least in real data and whatnot. So this is the main part of the talk. So of course, whenever you publish something, there are going to be skeptics. And the talk that I'm going to give is the rest of the talk, that are the skeptics right? So what is the skeptics, what are they saying? So these are the two papers that have been published, Hestian, Fithian in 2013, and there was a paper in 2015 in Methods in Ecology. And there is another paper that is submitted to me. The author sent it to me, but I cannot tell you what, I'm not allowed to share their name. But their points are basically the same as these two papers. And so we gave the response in Solimos and Lele paper. You can look into it for more detail, but let me tell you where the big issues are. So let's look at statistical inference in a nutshell, because I think the comments that they are making or objections that they have has something to do about how we do statistical inference. And so in statistical inference, in a very rough way, what do we have? We specify a model space, collection of all models that you would consider as possible generating mechanisms. We have a divergence measure that measures the distance from the true generating mechanism to any element of the model space. Usually we use Kullback-Leibler that corresponds to likelihood estimator. And the estimation is, we find, given the data, we estimate the generating mechanism, and we find the element in the specified model space that is closest to the estimated generating mechanism. So MLE actually is the closest in Kullback-Leibler sense to the generating mechanism. And given the model space and the divergence measure, we can find out if the elements of the model space are estimable or not. So if two elements are equidistant from the estimated model, then they are estimated generating mechanism. So it is a non-parametric estimate. They are non-estimable. If the generating mechanism is, the true generating mechanism is equidistant from two elements of the model space, they are non-identifiable. So that's just the basic question. So we make sure the parameters that we are using are actually estimable. Otherwise, you could be doing completely hokey result. And so we should base it on estimable parameters. Completely important thing to think about. So here is the gist of the criticism. So I'm going to denote by M0 the RSPF class of models for detection and occupancy, which is M0 equal to pi x beta and delta z theta. I will be here in a second. I just wanted to see what time it was, sorry. So I have a few more minutes, I'm not running out. So this is the RSPF class, which is M0. What they do is they expand this model class to allow for scaled link functions. So they say M1 is a class, good enough, which is take your class, multiply it by C1 and C2, such that C1 is bigger than 0 and it is less than 1. So we get those constants so that the probabilities remain smaller than 1. This condition, of course, implies that actually C1 will depend on the covariates and the particular parameter value, but they consider it just a constant. Fine, whatever it is. Now, given those, here is what they claim. And I think it is correct, mathematically it is correct, that if the true model lies in the class M1, single survey methodology will give wrong estimates of abundance. Sure. Because anytime the true generating mechanism is not in my class, whatever class I consider, I'm going to get only an approximation to the true model, not the true model. And surprisingly, given this, the authors conclude that single survey methodology does not work when the true mechanism is in class M1, which could be outside M0, and hence should never be used in practice. And that seems to be bizarre, because if that is the case, almost all of statistics we should worry about, because most of the times the true generating mechanism is not in your model class. You almost always miss covariates. I can guarantee you that. And so this was kind of bizarre to me, that saying that this should not be used or the constraint is too much, because if that constraint is violated, you cannot do the good job. Well, yeah. And so this was our response. The first thing that, yeah, it is mathematically true and also trivial, because the expanded class does not satisfy the condition. We knew it, and we told the user when not to use it. Of course, do we know if it satisfies condition or not? No, we never know if our true mechanism actually satisfies all the conditions that we put in our results. So all of our mathematical theorems are of the type, if this is satisfied, then something happens. This is just pure logic. And obviously, if you violate the conditions specified in if, the conclusions do not follow. And all statistical methods depend on the specification of the model space, data collection mechanism, and a divergence measure. If you change the model space, the statistical method may or may not work, depending on how far your model space is from the true mechanism. Is it a good approximation? Is it not a good approximation? Identifiability and all of those things. So identifiability and all those things work for that particular specified model space, not any model space, obviously. So if you change it, you may lose all the things that are available in the specified model space. Unless that new model space is a subset of the original model, of course, then it will work. So by saying that single survey method should not be used because it does not work with model space M1, our claim was that all that these authors are saying is that you prefer the model space M1 and do not like the specification of M0. Fine, I agree with that, that is fair. But that does not mean other people also should not like that specification. If you specify this is where it works, if you think that model space is too constrained, then don't use the method. It is completely specified when it works. What you need to argue is the practical relevance of the model space, not just I found a model space where yours doesn't work, but that the new model space is actually more, or at least practically relevant, and it is better than what I have, or needed than what I specify. You cannot just say I found a model space where it doesn't work. And so our argument was this: the space that we have M0 is used in practice in nearly all the papers on binary regression, not just in occupancy abundance surveys, in epidemiology, biostatistics, other ecological problems, and many other fields. It has proved sufficiently rich in practice. On the other hand, this scaled functions that they have, we haven't found any papers that use M1 as their model space. So if you look at unmarked or any of the strand, that's a package that people propose using closed population or open population situation. The only options that they have are the ones that satisfy M0. They did not put scaled links in there. If it was important in practice, they would have. So what these authors need to do, or what we claim that you need to do, is convince the researchers that specification of M0 is deficient in practice and it is practically not useful. And I don't know if I can say that M0 is practically not useful when we see 70 years of binary regression. So I'm somewhat puzzled by that argument. And of course, it will be great if a method works in the expanded model, but to do that, we may have to add more assumptions. For example, you have to add closed population assumption, or you may have to, if it is open population, you have to add assumptions about how migration happens, immigration happens. So those are additional assumptions you can put in. Then you can work with the expanded model, sure. But are those assumptions testable in practice? Not really, not always. They may not be untenable or not testable. And so would you prefer to work in the expanded model class with these assumptions that are untestable and untenable? Or would you say, okay, I'm willing to accept M0 because I can see the assumptions make sense? And for multiple survey method with closure assumption, it works, but maybe the closure assumption is not satisfied in practice. And there is no practical method to test the assumption either. We know, one can do significance tests, but we know the insignificance of significance tests. Generalized versions, again, it has the same issue. You add assumptions and they are not always tested because immigration is not observed. And so I don't know what the model is. I just put in and hope it is right. And that's about all I can do. So single survey method relies on far less assumptions, but restricts the class. So it's a choice between what assumptions you are willing to live with and what class you are willing to live with. And you cannot say, because it doesn't work there, I will accept untenable, untestable assumptions because I like that class. Okay, you can, but doesn't mean the other method is useless. You really have to show that M0 is useless class. So the question becomes, should we? I think it is a question of parsimony and robustness. So the only way to answer this question is to apply these techniques in real life ecological situations and see what happens if M0 and M1, which one is. So we are working on that currently. And robustness under different methods. So even if you assume M0, sometimes you may get robust inference because you may have a violation of the closed population assumption, and M0, single survey doesn't need it. So it is like a marginal model applied to the replicate surveys. And you may get robustness the same way GEE gets robustness, the generalized estimating equations approach in epidemiology. So there are choices to be made. That's our point, that you cannot say this happens and hence should not be used. But there is a much more fundamental philosophical problem with the arguments made by these authors. And the problem is something like this. They are saying that expand the model space such that something happens, something bad happens, and then you should not be using your method because in the expanded model space, your method doesn't work. To me, I can launch this kind of a criticism to any statistical method in this fashion. So tell me your statistical method, tell me your assumptions, and I will find a model space that violates those assumptions, and hence your method is not going to be valid in those. And then I could say, well, it doesn't work there, and I think that is important without saying anything, why, and say your method is bad. It should not be used. I don't understand how one can argue that. So basically, Another thing that these authors claim in response to our response, they said, well, yeah, we know all methods depend on assumptions, but those assumptions should be testable. And their claim is, how do we know the true mechanism belongs to M0? Well, you don't. You don't know if your true mechanism belongs to M1 either, or any model space that you define. It's just a construction that we make. We hope it belongs, but hell, I don't know if it belongs or not. I can only say I get the best approximation. That is why we say all models are approximations, or wrong, but they're approximations. So we never know this. So I find that criticism to be puzzling and not very convincing. So the reality is that for most methods, it is impossible to check all their assumptions. So I just gave number of examples. So for example, latent structure models, mixture models, state space models, hierarchical models, they all belong to similar class. That's why I put them together. There is no amount of data ever tells me about the validity of the models of the latent variables. They don't have any physical meaning to it. And we use them. In a mixture model, it is non-identifiable problem. We make it identifiable by stating what the one component is, and then you can do all kinds of things. But if you are wrong in that component, you are wrong in the rest of the situation. As I was talking to David just now, that what that available distribution is in the habitat selection, what's the background data is, I don't know what is the correct one. Should I use the entire Earth as my background? Should I use Australia as the background? Should I use Canada, all of Canada, or only Alberta as the background? All of those are acceptable, and we say, oh, well, that doesn't make sense because. So it has nothing to do with, I cannot say anything more than I think it is right. And you accept it based on that. So same way, I cannot say if a sequence of numbers, are they coming from IID random variables? Well, I can give you a sequence that comes from a deterministic sequence. As we know, in random number generation, it is a deterministic sequence. And you cannot tell me the difference between that and IID random variables. And that's why we can use it for simulation. And so you cannot check quite a few assumptions. And so how can you say that you should know whether the truth belongs to that or not? The only thing you can say is that the restriction is not good enough, and then you have to justify it in terms of practice. And so our argument is that every method depends on assumptions, which is part of the choice of a model. Not all assumptions are testable directly. The choice could be based on robustness of conclusions to violation, and also on how likely is it that a particular assumption is violated. So how likely is it that closure is violated? How likely is it that I don't know anything about immigration? How likely is it that my occupancy and detection is a scaled version or exponential model? And given what we know, I'm saying that M0 has been used a lot and it has worked quite well so far. So I cannot say that M0 is violated a whole lot, whereas there is a much bigger chance that other assumptions are violated. So why don't we do this marginal modeling and use that as a robust version? If the closed population assumption is correct, I will get correct answers using single visit, but I won't be as efficient, and because I'm not using the full power of the model. But sometimes robustness is important as compared to specifying the full model, the same way GE is useful. And so I'm kind of puzzled by the arguments that three people made it in a row, but it's essentially the identical argument. And some of the authors are common in these, and they are related to each other, somebody's postdoc and things like that. So I don't know if it is coming because it is the same group. But unfortunately, our critics remain unconvinced. I don't know what I can say. They are perfectly happy to use latent variable models where checking the assumptions is impossible. In fact, some of them made their name by using latent variable models. And in this situation, I think there is a substantial evidence for the usefulness of M naught. And they say, we are not convinced that M naught is good enough. Anyway, so I want to just conclude from what I said. So that's a puzzle that I have. And the conclusion is that if you have detection error, try to design your survey so that there is very little detection error. If there is detection error, you could use single survey or replicate surveys. Each has its own limitations. Single surveys might be more robust in one way, not so robust in some other ways. Replicate surveys might be robust in one way, not robust in some other ways, and you have to decide which assumptions are more likely to be violated in my particular study. And based on that, you can decide which of the methods you want to use, rather than saying this is never to be used, that is never to be used. Just as I say, replicate surveys are fine if you believe those assumptions are good. I have no problem with them. But you should know the limitations, and we have made it clear in our papers what the limitations are. So be aware of them, as we say. So every statistical method comes with the warning of caveat emptor, buyer beware, and so be cognizant of the assumptions, whether stated explicitly or implied. So that's my conclusion. I don't quite agree that we have to throw away single survey because it doesn't work in M1. I think M naught is a fairly wide class, and I don't quite get the critics. So that's it. Thank you.
Thank you, Subhash, for a great talk and some good discussion on possible different point of views from the approach. Given the time, maybe are there any quick questions or comments for Subhash?
Hi, it's David here. Yeah, thanks for your talk. Yeah, it was a quick comment, I guess. Andy Royal and some collaborators proposed something that looks kind of related to this in the presence-only context a few years ago. And yeah, they got some criticism for it as well from Trevor Hasty. And I was just...
Oh yeah, I know.
Yeah,
his Maxent paper, right?
Velocity.
Max-like, what they call.
Yeah,
but it's basically what I did in RSF paper, basically. It's the same algorithm that I published in 2006 in the RSPF. Yeah, I know yeah. So in our paper, we talk about it. I could not talk about it in this presentation given the length, but it's the same issue.
Yeah, so as I understand it, sort of one of the main issues that Trevor's concerned about is that, yeah, technically you can make something not identifiable by changing the link function, but it could be close to unidentifiable. So like a logit is close to a log in a lot of the range, particularly so for rare species, for example, for small p, a logit function is basically a log, and so so although these functions look quite different. At parts of its range, and parts of its range that are often ecologically relevant, they're close to log linear. So I guess that's kind of the argument. We're making an assumption which gets us out of trouble, but it keeps us close to trouble.
So there are two comments that I can give you. One is for occupancy and detection. Usually does not seem to be the case. One thing, at least given the data that we have seen in the past. And if it is close to that, it is similar to saying that, well, the linear regression is bad if the covariates are kind of correlated, but not fully. So it shows you it will give you, if you do the inference actually fitting, it will tell you that some of the parameters are extremely variable. And if they are that uncertain, I know I cannot trust those parameters. So I don't understand what the...
Yeah.
Doesn't that happen in real life, that sometimes your data are such, or your model is such that certain part of the parameter space has the Fisher information matrix varies according to the parameter space. So
I think we can use the linear regression analogy for this. So the linear regression analogy is that if you've got predictors that are perfectly correlated, then it's unidentifiable. You've got a single defined matrix. And so maybe we shouldn't use really, really highly correlated predictors, which give us a near singular design matrix.
Right. Yeah.
And so that's kind of the argument. It's like, no, we shouldn't, you know, sure, technically it's possible when it's not exactly singular, but that doesn't mean it's a good idea. I think that's kind of the argument.
Quite agree, but the point is that I can tell you when to use and when not to use, just as in regression. If it is close to singularity, your variance estimates are so high that you say, hell, I cannot deal with this.
Yeah, right. Cool.
And so there is a flag, is my point. And those issues may be true in the RSF situation, and that's why I have problem with the RSF, RSPF, as I talked to you earlier, for various reasons. But in occupancy and detection issue, I haven't seen it being that close to linearity.
Okay, sure. Thank you.
Yeah.
Anyone else for a quick comment? All right, so I think given the time, we're going to thank Subhash again for the great talk. So
Thank you.
Tapping on behalf of everyone. If anyone wants to stay on the line and have a chat with Subhash or just say hello, Subhash is happy to stick around for a little bit. So I'll stop the recording for now.